Section 11.2 starts our discussion of curves, properties of curves, and some discussions of symmetry. So the first thing we're going to do is, again, we've got a lot of vocab in this section, and some of it you may or may not remember very well, and so some of this is going to start to look a little bit less like things that you used a lot, and so maybe remember as well. So the first thing is to describe what a curve is. So a curve is an object similar to a line that's in a plane. The easiest way to think about it is that it's simply a path that's drawn on paper. So if you can take your pencil and you can trace along it, or you can create it with your pencil, it's a curve. There's different ways to sort of define or describe what curves do. One is to call a curve connected. So a curve is connected if it can be drawn without lifting your pencil. That is, if there are no breaks in the figure. So taking a look at these objects down here, which of them are connected? The first one's actually connected, I think, unless it's drawn. I mean, I don't see any breaks in it, do you? Can you start somewhere and actually draw it from one end to the other end without actually lifting your pencil up? Yeah. So this one's connected. How about the second one? Yes, the second one is also connected. Right? I could trace around it without picking up my pencil. How about the third one? Yes. And the fourth one? No. What is it about the fourth one that causes problems?
The dashes.
Yeah. So this one, we'll use a big giant red X if I can find my red. This one is not connected. Those dashes, that requires your pencil to be picked up and put back down. So don't fill in the gaps of what's not there. We tend to do that sometimes too. All right, another description that we can talk about when we talk about curves is the curve being simple. A curve is simple if it does not cross over itself. So, the first object, is it simple? Yes, it is. How about the second one? Yes, it is. The third one? Yep, also simple. How about the fourth one? No, this one is not simple. This one has failed now twice. Apparently I just need a red pen because this red line tool is not working for me. So let me do that. All right, it is not simple. So we have the ideas of being connected and being simple. We have a couple more. Our next idea is the idea of being closed. A curve is closed if it has the same starting and stopping point. Okay? So we're actually going to go back to the slide before and decide which of those objects are closed. Starting and stopping point are the same. So if your pencil starts and stops at the same place, it's considered closed. Is this first one closed?
No.
No. It is not. Is the second one closed? Yes, it is. How about the third one? Yeah, it's closed. Let me use this one as an example to show it. So if it's closed, it means if I start right here and I trace without, I get the entire thing traced, I stop at the same place that I start. How about the last one? Yeah, it is, right? We have this sort of weird disconnect kind of thing, so we keep starting and stopping multiple times, but especially if this were connected, right, we would see that this would start and stop. The crossing over itself is not a problem, right? Okay, so we would consider this to be closed as well. A polygon that is simple Okay? What was simple again?
It
Doesn't cross over itself. And closed, which means it starts and stops at the same place, and whose sides are line segments, that kind of an object is called a polygon. So the first two examples right here are polygons, right? They're simple, they don't cross over each other, right? They start and stop at the same place. These are considered polygons because they have line segment edges. I didn't draw that last one very well when I was chasing it, but they have the line segment edges. These last three have some sort of a problem with them. What's their problem? They're dashed. They're not connected. So why does that fail the description, though? Because this description said simple and closed. It didn't say connected. What part of this tells us that we have the issue with these particular three pictures? Do you know? It's what? It is a curve. It's a non-connected curve. It's what? The line segment part. Remember it said that the edges had to be line segments? These edges are not line segments, right? Because line segments would be the entire edge, if you will. There's these gaps in it, so that's caused these problems. All right, a couple more. Convex and concave. So a convex curve is simple, closed, and its interior contains any segment drawn between 2 points on the curve. And concave is probably my favorite definition, maybe ever, maybe not, but it's definitely a fun one because basically it says it's all those things and it's not convex. It's just the opposite. I mean, it's just saying, okay, and everything else, we're going to give it this name. We're going to give it the name concave. So what we have to be able to do is we have to be able to take 2 points on the interior and check to see whether or not we stay on the interior. So if I took these 2 points and I connect them with a line segment, am I still completely inside of the curve? Yeah, I am. But is there a way in this particular diagram that I could take 2 points and that wouldn't work? Yep, there is. What if I take, come on, what if I take this point? And I try to connect them with a line segment. And when I do that, I cross outside the curve. Well, if that happens, we have something that's concave. Okay? If it's not possible for that to happen, then it's convex. All right, so let's take a look at this particular diagram. It's simple and it's closed, right? It's not connected, but it's simple and it's closed. Any 2 points I take inside of this object, will the line segment be inside of the object? Yes, it will. There's no way that I can do what I just did on the last problem, right? The last diagram. I can't do that. This one is considered convex. How about the third picture? That one's concave. Can you show the picture? I mean, can you see the dots that are going to sort of make it fail? They'd be dots down here, right? So this one is concave. How about the last picture? That is convex. Okay, so let's talk a little bit more about polygons. We introduced them the slide before this one. Polygons are classified by how many sides they have. And the number of sides is going to be the same as the number of angles. So you could say the number of angles they have as well. That would be all right. But the number of sides or angles, which is the same as vertices that they have. So if you have 3 sides to an object, I think you know what that one's called. What's that one? That is a triangle. Do you know what the 4-sided object is called? Quadrilateral, very good. Quad, like quadruplets. How about 5 sides? Nice, you guys are remembering very well. Pentagon. Do you remember a 6-sided figure? Hexagon. You did hesitate a little bit there. That was still, you got it, good, hexagon. I should have brought like candy for if somebody remembers number 7. Somebody did. Heptagon, very good, Emma. Yeah, I heard a couple of you. Heptagon. Nobody gets a treat for 8. What's 8? That one's an octagon. I'm going to be impressed if you remember 9. It's a nonagon. I am impressed. You really like never see this one. They never even do, examples with it or anything. Nonagon. Do you remember 10? Decagon. Decagon, right. There are sporadic names for objects that are larger in size than this, but these are the ones that we see used most frequently, the 7 that we see used. So they're the ones to keep in mind as you see objects. When we give names to our polygons, we name them by the consecutive vertices. They have to be done in order, all right? So this object right here is called a quadrilateral, right? Why? 4 sides, or there's 4 vertices, or there's 4 angles. We can give lots of names for this quadrilateral, but there are things we cannot give it a name and actually be correct on as well. So somebody give me a name of the quadrilateral. A, B, C, D. Somebody give me one other option.
B, C, D.
Okay, B, C, D, A. Now I'd like for somebody to give me one that we're going to mark out in big bold red and say this doesn't work.
B, D, C, A.
What is wrong with going B, D, C, A? It doesn't go in order. I skipped from B to D, which did not actually, I couldn't do that unless if I were really going around this object, like walking around it or tracing around it, I would have had to have passed through either C or A to do that. So that object would not work. In particular, what happened when I went from B to D is I went through a diagonal of my object, in this case a quadrilateral. So a diagonal of a polygon is any line segment connecting non-consecutive vertices of the polygon. So if I go from B to D, that was not good, let me try that again. If I go from B to D, if I make it large enough on my screen, I might be able to connect them. B to D, that would be diagonal. What's the other diagonal in this one? CA or AC. So there are 2 diagonals here. So here we have diagonals. B, D. It's a line segment, right? And CA. So let me ask you a question that we encountered last time and see if you remember. If I fail to put the line segment on top and I just write BD, nothing on top of it, what does that mean? The length or distance, right? So keep that in mind. A diagonal is not a length or a distance. It's actually an object, a physical object, the line segment itself. Okay? All right. One more. I'll ask you one more question, and then we'll let you go. Draw a triangle. Just draw one on your paper, and give the vertices names, whatever letters you like. What I want you to do is I want you to write down all of the diagonals of your triangle. What did you find? There aren't any. Why not? Yeah, everything is connected to the other points, right? There's only 3 vertices. They're only connected, they're always connected to every other vertice on there. So there are no diagonals in a triangle. Every other polygon there are. And we will have a formula at some point for the number of diagonals in a polygon as well. So we'll stop there for today.